So in this video, we're going to talk about springs. And springs store mechanical energy when they are compressed or stretched from the rest position. So for example, let's consider the spring here on the illustration on the right. In this case, on one end of the spring, we have some heavy object, and the weight of that heavy object is exerting a force which will stretch the spring. So this will be kinetic energy being converted into potential energy. Now again, remember, springs store mechanical energy when they're stretched or compressed from their rest position. So the more kinetic energy that's used to stretch or compress the spring further, well then the greater the buildup of potential energy. Now, after the stretching and compressing has been done, something different happens. So for example, again in our illustration, if we were to say remove this weight, remove the force being exerted by this heavy object, well then we don't have kinetic energy being transferred to potential, but in fact we have the other way around. We have the stored potential energy converting back to kinetic energy as the spring returns to its rest position. Now, the force that's exerted by a spring is governed by what's known as Hooke's law. And Hooke's law says that the force is equal to the spring constant, and this is of course a constant that will vary from spring to spring, and the extension. And the extension is simply the length or the amount that the spring has been stretched or compressed. And importantly, for constant force, the extension of the spring is inversely related to the spring constant. So this is to say, if we have a large spring constant, well then we have a stiff spring. So we will be able to extend the spring less, or at least it will be more difficult. Now the opposite is also true. So for example, if we have a small spring constant, well then we're going to have much more extension, and the spring will be much easier to extend. Now, of course, springs are used in countless tools and machines, many of which we probably don't even know. There are some obvious ones like car suspensions and mattresses. We all know the spring mattress. But then there are other examples that are lesser known, like ballpoint pens. Springs are everywhere. So now let's talk about the different ways that springs can be combined and used together. So in general, there are two types of arrangements. We have the in-series arrangement, and we have the in-parallel arrangement. So let's break them down one at a time. So we'll start with the in-series arrangement. So in-series arrangement refers to springs that are connected end to end, or in other words, they are force sharing, such that the total stiffness is reduced. Now let's consider what implications this has for the spring constant, which, if we remember, is a reflection of the stiffness of the spring. Well, in this case, we have this relationship where we have 1 over the total spring constant is equal to 1 over the spring constant of the first spring plus 1 over the spring constant of the second spring, and so on. So again, there is a total reduction in stiffness. The total stiffness will be less than that of the spring that is stiffest. Now, the big takeaway, I suppose, is that greater displacement compared to individual springs. Because again, we're reducing the stiffness, which means therefore it's easier to extend the spring and we can extend it farther. So we should expect more displacement for the same force. Now let's compare this to the in-parallel arrangement. So in an in-parallel arrangement, springs are connected side by side rather than end by end. And now note that this is side by side, not side to side. So the springs themselves aren't directly connected, but they are configured parallel to one another. So in this case, they share the same displacement. We couldn't have this first spring displace any less than this second spring, which is not true of the in-series arrangement. So in this case, the total stiffness actually increases. So for the spring constant, we have the K total is equal to K1, the spring constant of the first spring, plus K2, the spring constant of the second spring, and so on. And the result is less displacement for a given force compared to individual springs. Again, in this case, the system is stiffer, so therefore we should expect less displacement for the same force. Now again, we can summarize these key differences, the takeaway of this information, which is that arrangement in series reduces stiffness and increases flexibility, whereas an in-parallel arrangement increases stiffness but decreases flexibility. So now let's talk about spring overextension. So this is where we go beyond the point where the spring can be expected to return to its rest position without deformation. So there are three main parameters that can influence spring overextension and the likelihood of spring overextension. We first of all have the number of coils, we have the outer diameter, and the wire diameter. So again, let's go through these one at a time. First of all, in terms of the number of coils, we can take an example here on the right. So this top spring, at least relative to the other springs, has more coils. It is composed of more individual coils that constitute the total spring. So when a spring has more coils, it allows for greater extension and an increase in the extension tolerance, or the overextension tolerance. But conversely, fewer coils reduce extension range and will overextend sooner. So if all else equal, and we had a spring of this length compared to a spring of this length, well, again, if all else equal, the top spring, the one with more coils, could extend further without overextending. Now, secondly, we have the outer diameter. And the outer diameter refers to, of course, the outer diameter. But let's visualize this just to confirm. So the outer diameter refers to this dimension here. Now, for a smaller outer diameter, this will increase stiffness and limit extension, whereas a larger diameter decreases stiffness, allowing greater extension before overextension. So again, for example, here in this middle spring, we have a smaller outer diameter compared to the bottom spring. So for the bottom spring, which has a larger outer diameter, again, if all else was equal, which of course is not the case in this example, but if the only difference between the two is the outer diameter, well then this larger diameter spring will have decreased stiffness and could be extended further before overextension. Lastly, we have the wire diameter. So this is the actual thickness of the individual coils, or the wire that's used to make these coils. So again, we have a similar relationship where the thicker wire increases stiffness, as you might expect, and therefore resists overextension, whereas the thinner wire decreases stiffness and makes overextension more likely. I would say this is the most intuitive of the three. It's easy to understand and again intuit that a thicker wire would be stiffer, and therefore the stiffer, the more difficult to overextend. And again, we can see a characteristic example of spring overextension here. And if we're trying to diagnose what the likely cause is, or what may need to be increased in order to make overextension more likely, for example, we could consider these three overextension parameters to design a more efficient tool or machine. So before we wrap up, let's talk about the three main types of springs: extension springs, compression springs, and torsion springs. So let's start with extension springs, which are also often called tension springs. And extension springs stretch when a force is applied. So for example, if this were to be pulled from either end of the spring would stretch, and it would stretch as a result of those forces. And by resisting those pulling forces, the extension spring can store energy. And two common examples of extension springs in everyday life are trampolines and garage doors, among many, many others. So the second type of spring is called a compression spring, which is essentially the opposite of the extension spring, because compression springs compress under a load to store energy. So again, we have extension springs, which stretch when a force is applied and thereby store energy by resisting the pulling forces. But again, compression springs do the opposite. They are not stretched, but they are compressed. So the direction of those applied forces is opposite towards the spring, compressing the spring. And by resisting the pushing forces, not the pulling forces, the compression spring functions to store energy. And like the extension spring, compression springs have many applications in many different machines, with two common examples including pens and shock absorbers, such as what would be found in a car or off-road vehicle. Then lastly, we have probably the least common of the three main types of springs, which is a torsion spring. And now a torsion spring will twist to store rotational energy. So again, the extension spring is resisting those pulling forces to store energy. The compression spring is resisting the pushing forces to store energy. And the torsion spring will resist torque. So again, these are rotational forces, rotational energy. And the torsion spring also has quite a few common examples in everyday lives, with 2 examples being clothespins and mouse traps. Let's review some of the key information from this lesson. First of all, springs store mechanical energy when they are compressed or stretched from the rest position. So when this happens, we are taking kinetic energy and converting it to potential energy. We are storing mechanical energy. But when that force is removed, the opposite will happen. Potential energy will be converted to kinetic energy as the spring returns to its rest position. The force exerted on a spring is governed by Hooke's law, which says that the force is equal to the product of the spring constant and the extension. And remember, we're talking about this fundamentally because springs are useful, and they're used in countless tools and machines, some obvious, some not so obvious, with a few common examples including car suspensions, ballpoint pens, and mattresses. Springs have 2 different arrangements in general when they are used together. We have the in-series arrangement, which reduces stiffness and increases flexibility, whereas the in-parallel arrangements increase stiffness and decrease flexibility. Lastly, we talked about overextension. So this is when a spring can no longer return to the rest position without some type of deformation. And in this case, there are 3 main parameters, which include the number of coils, the outer diameter, and the wire diameter.